Now let's come back to solve the real problem. And do you remember we start with a block of mass m, and let's say its simple case is there's only one force. Actually there are a couple of forces, but we can focus on that dragging force. The dragging force has an angle theta with respect to displacement delta r from this picture. So from what we learned, the work done by this F, defined as F of dot the displacement, and according to what we know, the definition is the first vector's magnitude, the second one's magnitude. In our case, it just say force is how many Newton and displacement how many meter, times cosine, the angle between them, that is cosine theta. So the work done can be easily calculated. I want to point out one thing, and if you combine this F and cosine theta term, what is F cosine theta? F cosine theta actually is the F of x component. So if we name it, that is F of x. This tells us the F of y term does not do work, because the Fy term, when Fy term dot the displacement delta r, the Fy is perpendicular to delta r, so cosine 90 equal to 0. Now, in our case, we have more forces. This is normal force, this is dragging force, this is gravity. If we add one more force, which we say kinetic friction, you remember we have 4 forces for our first example. How do we calculate these forces? Well, I want to show you the two force perpendicular to displacement delta r. Work done by gravity equals to gravity dot delta r. Now, the definition is magnitude of gravity, magnitude displacement, cosine, the angle between gravity and delta r is 90. That equals to 0. So when a force is perpendicular to the displacement of an object, this force does 0 work. So similarly, that work done by the normal force will be 0, because it has an angle 90 degrees with respect to delta r. However, that the force of Fk is slightly different. That is Fk dot of displacement. In this case, Fk's magnitude, displacement, cosine, the angle between Fk and delta r is 180 degrees, because delta r is to the right, Fk is backwards. So that is cosine pi. That results a negative Fk dot delta r. Now let's look at our situation. That the work done by this force, the dragging force, is positive. The work done by gravity and normal force both are zeros. The work done by kinetic friction is negative. It is very interesting that, first of all, next time when we solve a problem, if we know that particular force has a 90 degrees angle with respect to displacement, we do not even have to calculate the work done by that force, because it's 0. Then when you know that the work done by that force is positive, actually that is the force caused the motion. When you have the work done by another force, if it's negative, this is the force oppose the motion. Friction actually is against the motion. So positive work done by a force, which means this force is the reason that objects start to move. And if the work done is negative, and then that force actually is against that kind of motion. We're all talking about work done by a constant force, but what if work done is by a varying force? For example, in this case, you see, force versus displacement is not a constant. It changes its value. So you remember we have that work done, actually general definition is F dot ds. Only when the force is a constant, then we can pull this force out of the integral, and together with this dot, and we have summation of ds. All the ds add together, that is the total displacement s. So this is good for when a force is constant, when F is constant. Be careful, force is vector, so when we say force is constant, which means both direction and magnitude have to be same all the time. That means it keeps a constant. But if force is not a constant, then we cannot do this kind of operation, so we have to follow the general definition that F dot ds. So we have to cut a slice of it, because during a small displacement, in this case we use delta x, that actually equals to ds. During a very small move, well, force actually changes when a position, when we have displacement. But when we have a very small displacement, force almost remain a constant value, which is somewhere that here. We can actually, if we have scale along the fx, we can read what is how many Newton. So when we use that height, which is the value of force, times delta s, because that's the value of force, times that ds, what we get is the area. So F dot ds give us that area. Obviously we have to take care of a dot first and see whether the force and displacement holds an angle in what way. But in this case, fx is positive and your ds is positive, so that means they are at the same direction, so the angle is 0, cosine 0 is 1. That's why fds just end up at f's magnitude and times ds magnitude in this case. So the sum integral means summation. Summation, that means they add all the slice of area. So eventually the total work done is the area under the f versus x curve, starting from initial position to the final position, because this is a displacement. Displacement integral is always start from initial position to the final position. Here is an example of force varies when the position changes. This is a mass spring system. This is a spring with a spring constant K, and this is the mass, a block mass sits on the floor. If, let's say, ignore other forces, when the block, this is at x equals 0, and spring has no, not being compressed or stretched. But look at the other two positions. When the block is on the right side, the spring has been stretched. So there is a elastic force from the spring. The spring tried to pull the block back, and that force is point to the left because it tried to pull back. And when the block is on the left side of origin and the spring is compressed, has been compressed, the spring tried to push it back, so the force is to the right. So we say Fs is positive when x is negative. The other one, Fs is negative when x is positive. Now we know that from Hooke's law, actually that force is proportional to the displacement, which means the bigger the displacement, the bigger the elastic force that the spring will try to pull the block back. So this F and verse x is proportional. This negative sign means forces are always at opposite direction of displacement. This is when displacement positive, Fs negative, and the other one when displacement is negative, Fs positive. So if we plot Fs versus x, that is that straight line. Straight line means it's linear. Fs versus x is linear, and the slope is negative, so that's why the straight line going this way. Now, this is a force that varies when the position x change. So what we do is we say what we want to calculate work done by this f of s. That equals to f of s dot dx if we talk about only around moving around x direction, right? So according to the definition, the fs is always at opposite direction of dx. So we say it's negative when we do dot. Why is negative? Because that is fs magnitude and dx magnitude cosine 180. That is negative. So we still keep that. This negative sign is because cosine 180. Okay? And then we plug in the magnitude of fs that is proportional to the x. So from x of initial to x of final. So this is the integral that we can deal with because k is spring constant, it's constant. X dx will give us 1/2 x squared. So the result will be, first of all, we still keep that negative sign, and the result is 1/2 k of x squared from that initial position to final position. That is how much work has been done by the spring.